But this is the most important application of the force of gravity in Newton's second law, is all about the elevator. Like I said, for standardized tests, it's the go-to question. And that's why we do the activity that we would do to center around it. So I looked for some new force diagrams to kind of show you, because normally I would draw a lot of this stuff on the whiteboard. But here's an elevator, right? The guy's standing on a scale inside the elevator. And so Fs is the force of the scale upward. I don't know what they're making FP be, force of the person pushing down on the scale, I guess, because of his weight. We would just draw this as W down. Man, that's kind of, yeah, it's interesting. Tension is up, right? Force of the FP maybe is the force of whatever they're calling his elevator. But essentially, as it shows here, the system of interest is the person standing on the scale. The scale is pushing up, the force of gravity is pulling down. Now, the confusing part is this force of scale right here. This is going to change because of the motion of the elevator, right? It's reading this. This falls into the category of a normal force, right? It's the scale exerting that force. So this is changing. This reading is changing. Your weight is not going to change while you're riding the elevator, but whether or not you're accelerating, upward or downward, well, it's just getting worse and worse. That's going to determine, or if you're moving at a constant velocity, that's going to determine how much more force or how much less force the scale is going to exert on you, right? If you're on a really good elevator that accelerates very quickly, and so you go fast very quickly in a short period of time, or you come to a very abrupt stop, the scale reading is going to change significantly from your weight. But when it's at a constant velocity, right, when all forces are balanced, then it would read your weight, even if you're moving. So, right, I forget where I found this one, but I liked his picture. When you step into an elevator, you feel like you're the same weight you're waiting in the hallway. Obviously, you're not going to normally take a scale into an elevator. But if you were sitting outside the elevator, standing on a scale, so what we would do is I would have the scale sitting in the classroom. I'd say, all right, everybody step on the scale and get your weight in newtons. Then we'll put it on the elevator. Well, we have 3 of these that work. And so we'd have a couple groups going at the same time. You'd stand on the scale and you'd see that it reads the same as it would in your bathroom or in the classroom. And then we would hit go and the elevator would start to move. And so the normal force, as they list it here, right, is the force the scale's exerting up minus the force of gravity down equals 0. And so whenever the forces are balanced, then it's going to read your weight. And that could mean it's in your bathroom and your bathroom floor is not moving, because that wouldn't be good. And you're riding on an elevator at a constant velocity, right? And so what do you think happens when the elevator starts moving or accelerates either up or down? Well, if it's accelerating, this doesn't equal 0, it equals ma, which means this value is going to change, right? Based on whatever ma is, because now it's not balanced. And unfortunately, when we ride the elevator at school, the amount of time, and that's probably true for any elevator, the amount of time that you're actually accelerating is very minimal. But our elevator at school doesn't go very fast, but it gives some very good jolts. You definitely feel the acceleration, but it just doesn't happen for very long because we're only going 1 floor, right? So the first case to be considered is the easiest one. What do we have when we have balanced forces, right? So this is Newton's first law, because forces are balanced when you have a constant velocity. But you always start out with the statement of one of the laws. And the nice thing about the second law is you can always start with the second law and create the first law in one step, because your forces are balanced. And so if you have, right, you standing on the scale, that's you. We'll make it me with a couple pieces of hair, right? You've got the normal force up. That's the scale force. That's what we're reading as changing, and the force of gravity down. And so you would say, all right, well, at a constant velocity, we know that acceleration is equal to zero, right? And so the sum of the forces equal zero. And it becomes Newton's first law in one quick step. So the nice thing about it is you can always start every problem with the second law and make the first law once you realize that the forces are balanced and you have a constant velocity. But you would say the normal force, or this, you could call this Fs, force of the scale, minus the force of gravity equals zero. So therefore, that's true. It equals mg, right? So we're moving up or down, but we have a constant velocity, right? And then it's going to read the same thing as if we are not moving, right? Hopefully by now, after going over the first law for the couple days, you already knew that. Mathematically, though, this proves it, right? That the normal force or the scale force is going to read whatever your mass times g is, regardless if you're moving or not moving, as long as it's a constant velocity. And it doesn't matter if you're moving up or down, it reads the same thing, which is the bulk of an elevator ride is moving at a constant velocity. You would see that on the LabQuest, that if the ride took 60 seconds, um, most of it is constant velocity. So then what happens when you're moving vertically upward and accelerating, right? And so I don't know where the force diagram went to, but that's interesting. So now, again, the same scenario, I can draw a little bit better, right? That's me. So I'm moving vertically upward and accelerating. So now think about this. Here's the second floor. What we're going to do first, if we were here on the second floor, is I would push the button and then the elevator is going to accelerate down, and we're going to have, right, a negative acceleration. Then we're going down, and then as we hit to the first floor, right, meaning we're moving and then we're coming to a stop, that's actually a positive acceleration, right? So think about, how do we know whether or not, because there's only 4 cases, right? This case, what my case 2 here is we're on the first floor and we're going to accelerate up. That's a positive acceleration. And then here in the middle, we have a constant velocity. And then as we get to the top, right, we're coming to a stop, and that's going to be a negative acceleration. And so there's really 4 cases, but I kind of just went through the general case of what if we have a negative acceleration, what if we have a positive acceleration. How we know if the acceleration is positive or negative, other than maybe memorizing these 4 situations, comes from this equation, right? Or the equation on your AP formula sheet is this. In solving for A, is this 0 or is this 0? Right? Is your initial velocity 0 as it is here and here? But remember, downward motion is negative and upward motion is positive for V. So here you get a negative acceleration because you're starting from rest, but after that period of time, you have a negative velocity over time and you have a negative acceleration. So, but when we set up the problem, we're going to set it up in general terms. We have the normal force up, we have the force of gravity down. So this, I'm kind of looking at this situation right here. We're on the first floor and we're going to accelerate up. So my initial velocity is 0. My velocity here is a positive, right? And so when I solve for the acceleration, I have a positive velocity minus 0 over time, which gives me a positive acceleration. So that's on the first floor or any floor, but we're going up, right? The scale force is going to equal MA. I guess it's time to buy a new one of these pads. Maybe try a different company, right? It's going to equal ma plus the force of gravity. So let me rewrite this. The force of gravity plus ma. This is how much more force the scale is going to read because of the motion of the elevator, right? When we're moving at a constant velocity, this is the value. So if this is 500 newtons, it's going to be 500 plus your mass times whatever your acceleration is because you're riding the elevator. It's going to increase by that much. Now, that's the same thing as if you were lifting an object up, right? When you think about all the times you've picked something up, right? Whether or not you're in Mr. Townsend's or Chandler's weight class and you're lifting weights, you don't go down there acting all herky jerky and spastic lifting things because you're going to pull a muscle, right? And when you do it, you want to, if you're bench pressing, you're going to do it as smoothly as possible so that you can exert the least amount of force because you want this to equal zero and you want this to be the case that your force upward is equal to the force of gravity. If you try to do it and accelerate it, you're going to need more force to have that happen, right? If you think about all the times, if you've ever watched sports, when somebody pulls a muscle, or think about any machine that you've ever seen that you've turned on and it breaks, or you turn it off and it breaks, but it's usually on. That's when it's under the most force, is when it's accelerating, right? Because of this. Now, this force doesn't have to be the force of gravity, but people pull muscles when they're either starting their race or finishing their race, right? It's what we say when you're under load. When you go to turn on a machine and it starts and then it goes and stops, that's because that's when it's under the most amount of force. And that, for whatever reason, that was the time it was not going to be able to handle it and it breaks. It's not usually as it's going, because most things move at a constant velocity when we get them to go. That's usually not when things break. It's under that extra stress of, um, the added force of getting it to accelerate. Um, but in our case, our application here, right, the normal force or scale force is going to be greater because of that MA. And then the last case is what happens when it's the opposite, right? And so you're either on the second floor and you're going down, right? So one of the dangers is, and you'll see it when on the last slide, um, when you draw the force diagram for each case, if that was the case, and it's been a problem where it's giving you all three cases, and it's giving you graphs, and it's a bunch of different times on AP tests, the older AP test. You draw this the same every time, right? Your force of gravity again is not changing. Again, I don't know how long I drew it on the other one to know that, but I know in this case, the scale's going to read less force because we're accelerating down, and that's going to be a negative acceleration. And so when I put in my forces, right, this is where, if you're not calculating it and it's in a word problem, you have to know to make that value negative based on the situation, right? Going back to, and it doesn't have to be the elevator. It could be you lifting something up or lowering something down, to know that in either one of these cases, lowering something from rest, that's a negative acceleration. Having something moving up and coming to a stop is also a negative acceleration. So if you have to use this equation, hopefully the way you do it, it works out to give you that negative value. But if it's a word problem, based on the situation, you would have to know to make that a negative value. And then when you solve for the scale force, right, it's going to equal the force of gravity minus ma. And so now it's going to read this much less than your force of gravity when you have a negative acceleration, right? And so that's how much less it's going to read. So when you're riding the elevator, you would see that there's twice you're gonna seem like, geez, I've gained weight. You didn't gain weight, but the scale exerts greater force on you, and that's when you're going down and coming to a stop, and when you're at the first floor and coming up. Those are both positive accelerations. When we start on the second floor and go down from rest, or we're coming up, right, and coming to a stop, those are both negative accelerations. So the normal force in these two spots will read less force, and this would read more force. right? And so that just kind of summarizes what happens for you. We'll skip that based on time. Here's the force diagrams that I was trying to draw, kind of as a summary, which I stole this was slide was in the pre-lesson also. But here, the thing to notice, although this didn't, now that I see it big, this, right, this, and this should be the same size, but now that I see it on a big screen, it doesn't look quite to be as well when I was looking on my little laptop that I drew them the same size. But then also this should equal this, right? Because this is when you have no acceleration. This should be greater than the force of gravity here when you have a positive acceleration. And here it's going to be less than the force of gravity when you have a negative acceleration. That has been an AP question before, like I said, a couple times. AP has been around for physics for about 40, I think it's like 43 or 44 years. Now, in that amount of time, obviously things have changed a lot, but I think there's about 5 or 6 times where that's been one of the AP questions. It has not been since they've created AP Physics 1, but at some point it's going to be, and you never know if it would be this year. Oh, all right. I'd forgotten about this. I'm going to show you this next class at the beginning. You got, how many of you have seen the movie Up? It's it's a good movie, right? But there's great physics in here. But the great part about it is, man, people do some really dumb things. You guys have heard of the Darwin Awards, right? To earn a Darwin Award, you should look this up later. To earn a Darwin Award means you've you've committed the ultimate stupidity, and you've killed yourself, right? So that's not anything anybody ever wants to try to achieve. They tell us that if you've ever gone fishing, you can buy different strength fishing line. So if you're going shark fishing, you're not going to get like a 5-pound fishing line, right? It's not in newtons if at Walmart or wherever your fishing tackle place, but you would need something much stronger because you're catching a bigger fish. Um, so to make it go with what we're doing, he's using a 10 Newton strength line. Any fish that exerts a greater force than 10 newtons, whether it's weight or weight plus the motion, would make the line break, right? So he reels in the fish from rest about a meter in 0.8 seconds before he loses the fish. So that snaps. And he's like, all right, I was reeling it in, right? So the idea would be don't reel it in with acceleration, reel it in a smooth motion. That would put the least amount of force in the line to reel it in. What is the largest mass that he could have caught? All right, so let me go with the annotate because maybe it will make less mistakes. Here's the fish. Right, and he's reeling it in. So we're going to neglect any fluid friction, right, or drag through the water. So imagine this is underwater here, right? So you got the weight of the fish, and you've got the force of tension upward. We know that that force of tension can only be 10 newtons. Anything greater than 10 newtons and it breaks. We want to know what would be the largest mass that he could catch. Anything bigger than that, it would snap right away. We know that it's moving from rest. It moves 1 meter. You could use one y or x, and we know the time is 0.8 seconds. So now this problem kind of involves everything. That's why I chose this one and the idea of solving for mass. Whenever you're giving these numbers and you're not giving the acceleration, that's got to be a clue to you that you need to use one of these equations. In this case, you want the one with time and distance and not final velocity, right? And we need to solve it for A. Again, we know that that's going to equal 0. I'm going to solve this for A. Right, we've done that plenty of times. And so just kind of this this problem has that extra step. Probably the problem would just give you the acceleration and you would just have to know whether or not you make it positive or negative. Right, but I wanted you to see using those equations. So you have 2 divided by 0.8 squared, which gives us 3.125. So let's just call it 3.1 meters per second squared. All right, so now looking at my force diagram, right? The good thing is we have no x forces, right? There's no x forces in these problems when the object's moving up and down. So we do not need the sum of the forces in the x direction at all. We only need the sum of the forces in the y direction. That's the one benefit of vertical motion. I'm sure we can make some problems that have horizontal forces, but we don't need to. That's beyond our pay grade, so to speak. And so I have the force of tension up minus the fish's weight down equal ma. Again, to make the least amount of force, you would make this 0, right? So that would be a conceptual question, similar to like on the last test, that question with the what would make tension the smallest, what was the angle, what was the horizontal force, all that kind of idea, right? That what would make tension the smallest? Well, you want to reel it in with no acceleration. That's the smallest. Now you could say, well, what if you have a negative acceleration? But that means you're not catching the fish. The fish is taking it's going the other way, right? Which you wouldn't catch the fish doing that. Meaning you wouldn't be able to reel it in and have the fish in your hand. So here's the trick. The mistake people make here is they forget to include this. Because right now, if I want to know m, right, t minus w over a. This is 10, this is 3.1. Well, how do we calculate the weight? Do we know the weight? We don't, which means we have to plug in our equation. Can you solve the equation set up like I have it here? I'll give you a minute to process that. The answer is no, I can't, because I'm solving for m and it's here and it's here. So that's no good. So what do I do? Well, I got to erase that because it's wrong. Right? And so I need to look at right here, what do I do? Well, I'm solving for m, and you have to remember that it's, because this is the other mistake people will make. They'll put t equals ma. That means you've made the earth have no gravity, right? Substitute in, how do we calculate the weight? Well, it's m times g. Now you see you have two m's. So what did you learn in math class when you're solving for a variable, but it's in two places? You got to get them together, right? You got to combine like terms. So I need to bring the mg to the other side to make it mg on this side. So now I have ma plus mg. I'm solving for m. So now what do I want to do? We want to use the F word, factor, right? We want to factor. And because this is what I'm solving for, and it's in two places, so I want to factor it out. Now I can divide by, oops, sorry, I didn't make this m. We can divide by the sum of a plus g, right? And so 10 newtons divided by 3.1 plus 9.8 or 10, whatever you're using, meters per second squared. 10 divided by 13.1 gives me 0.76 kilograms, 760 gram fish, right? Probably like a little sunfish, bluegill, smallmouth bass, maybe. But so this problem has it all wrapped into one, meaning you have to use this. Not always will you have to do it. If acceleration is given, then we don't need the motion equations. But if it's not, you got to look to what equation from our three can find acceleration. We don't need the x forces at all. And then you're going to have some force always minus the weight equals ma, right? And so the only thing that's changing, if you're in the weight room today lifting weights, it's your force up minus the weight equals ma. It's always some force up or down minus the weight equals ma when you're doing vertical motion problems, right? And then this one's the hardest math one because it's that idea of you've got an m here inside this force of gravity equation, and you got the m there, and how do you solve for it, right? It's some simple algebra. All right, so